Okay, hopefully this works out. Not quite sure. Okay, anyway, there might be some issue in streaming. Hopefully it's working. And yeah, yeah, let's get back to teaching. So sorry for the delay. So last time we talked about determining system properties with this Laplace transform of impulse response. So we determine system property from this big H of S, that's the system function. And we see that we can determine the causality and the stability of a LTI system really easily. So for causality, it's a bit more complicated, but it says that if the system is rational, then your system is causal, if only if your ROC is right-sided, which means that the ROC include the right-hand plane extend to right infinity. Okay? And stability, LTI system is stable if only if ROC include its geometric axis. So you see that to determine the causality and the stability, it's very simple. You have a very simple criteria. The conditions here is just look at ROC. You don't even care about the algebraic part of your Laplace transform, so or system function H of S. You only look at the ROC, then you can kind of determine the causality and the stability. But certainly, for causality, there is this catch that for non-causal system, then this is only one-way direction. So if it's causal, then the ROC is right-sided. And we have seen a counterexample where the ROC is right-sided. But if the system is not causal, if the system is not rational, then this is not causal. So we need to be a bit careful here. Okay. But we'll mostly stay for rational functions. So ROC means right-sided. Rational functions. So causality means right-sided ROC, and the stability means containing this geometric axis. Okay, so now we go to what we will talk today. That's LTI system characterized by linear constant coefficient differential equations. So we have been talking about solving linear constant coefficient differential equations ever since I think chapter 2. And now we have a much more systematic way to do this. And for starter, we start with, this equation we get from convolution property. So from convolution property, we see that the Laplace transform of the output will equal to the Laplace transform of the impulse response and times the Laplace transform of the input. Okay? So big Y equal to big H times big X, and this big H system function is the Laplace transform of the impulse response small h of t. Okay? And now if we have a LTI system that characterized by linear differential equations, so linear differential equation we have seen it quite a bit of time look like this, and so we have our y of t and x of t related by those differential equations, by this differential equation. Then we can do Laplace transform on both sides, and just like in the Fourier transform case, this will factor nicely into something times big Y equal to something times big X. Okay, so this we just use the linearity and the differential property of Laplace transform to get the second equation. So differential property says that whenever you do a differentiation in terms of this Laplace transform, you just get a HRS. So you have kth power differentiation here, then you get s to the k here, and the linear combination just get a linear combination. So sum ak s to the k equal to big Y equal to this sum bk s to the kx. And then we move things around, so we know big H equal to big Y divided by big S, and so big Y divided by big S will be the summation B divided by this summation A. Okay. And so we look at this thing, we see that so this is so in terms of S, then this is a rational function. Okay. So that's why we care a lot about rational functions when we do Laplace transform. So this is a rational function of S. Rational function of S. So this is one of the major justification of why we keep talking about rational function when we talk about Laplace transform. That is because if you get a Laplace transform from solving linear differential equation, then we will get a linear constant coefficient differential equation, then you will get a rational function like this. So you see that the uppercase you have a polynomial in S, and the lowercase is a polynomial in S. Okay, and so the equation give you this nice expression for h of S. Then then you think back that we are solving differential equation. Then you think that we are missing something. Okay, so we are missing two things, and we will show the other same thing. We are missing something, that is we only have a differential equation, and remember before we said that to truly specify a differential equation you need auxiliary conditions. Okay, and this doesn't specify the system totally. You still need to have the actual condition says that. So sometimes you have initial condition or boundary condition for this equation to be actually a system. Okay, and another thing we didn't specify is ROC. Okay, and so we have the algebraic part of h of S that expressed here is a rational function, but from here we didn't see the ROC of h of S. Okay, and and indeed, so it's only the differential equation part doesn't tell you anything about the ROC of h of S. Okay, and so here we don't have the complete Laplace transform yet. We only have the algebraic part, and as we say, so the ROC part is actually determined by auxiliary condition or actual knowledge you know about the system. Okay, and so if we have additional knowledge about this system, say if we know it's LTI and stable, then we can pick the ROC for this rational function that include the j omega axis. And say if we know the system is LTI and the causal, then we will pick the ROC that's the rightmost ROC. Okay, just like the quick review we have. So we have a whole bunch. So the algebraic equation, we have a rational function. We'll get a whole bunch of points 0, and then the system being causal and stable, we will tell you that which ROC you should pick for those poles. So if it's causal, you pick the rightmost ROC. If the system is stable, then you pick the ROC that include the j omega axis. Okay, so this is how we solve the linear constant differential equation. Okay, and so for example, and if we want a more natural auxiliary condition, then maybe say one of the auxiliary condition we see a lot is this condition of initial rest, and we prove in chapter I think in chapter 1. Anyway, so we have proved that if we have a condition with initial rest, then the system will be LTI and causal. So LTI and causal, and for causality you can pick the ROC. Okay. And then if we have the ROC, then we have determined the full information about Laplace transform, and we can apply inverse Laplace transform. Then we can calculate this summa h of t, or we can calculate other things about the system. So we can calculate the input-output pair. Okay, and I guess here there is a slightly tricky part. Okay. That's not quite emphasized in the book, but I think it's nice to remember this. That is, all the analysis here, we assume the system is LTI. Okay? Actually starting here, we assume the system is LTI. We say it's a bit tricky. It's kind of starting from, we say, it kind of starting from here, the system is LTI, although you don't need the system to be LTI to transform the input and output, but for h of t to mean something, you actually need the system to be LTI, right? Remember, we have y of t equal to h of t convoluted x of t. This is, so this thing only happens when the system is LTI. So the whole analysis built from the system is being LTI. And the tricky part is the linear differential equation by itself doesn't say the system is LTI. Although it looks very linear and very time invariant, but you can pick some initial conditions such that this is not LTI. Okay, and so be careful when you want to do this whole part of analysis. You need to make sure that the system is LTI. And most of the example we do today just say we just hard code the LTI into the problem. We just say the system is LTI. But this is important because the later part of the course will be doing things that's not LTI in this chapter. Okay? And to avoid confusion, you need to remember that this Laplace transform analysis all assume the system is LTI. And that means you need to pick some auxiliary condition to ensure that the system is LTI. So for example, if you have the condition with initial race that we just talked about, then it not only guarantees the system is causal, it also guarantees the system is LTI. So condition with initial race system, we can solve very nicely with this Laplace transform. Okay. So this is a general idea. If you don't have a quick question, we can go to a quick example. Okay, so yeah, as we said, we have an LTI system. Okay, and now the differential equation look like this. It's a very simple first order differential equation. So dy dt equal to 3yt, dy dt plus 3yt equal to x of t. Okay, and here we do this a bit slowly, so we do Laplace transform on both sides, and as we said, so Laplace transform on dy dt becomes s times big Y of s, and then this 3y just Laplace transform to 3 big Y, and we have big X of s, and then we group big Y and the big X together, then we have h of s equal to big Y of s divided by big X of s. And then the remaining thing should be this 1 here divided by this s plus 3. Okay, so this is a really simple algebra. And now, as we said, this differential equation itself and with LTI only tells you the big H of s is algebraic part. It has a pole at -3, and it has two possible RLC. So you can have RLC that's to the right side of this pole or RLC to the left side of this pole. And as we've seen a lot in the inverse Laplace transform, this will give you two different time domain signal. So, time domain function. So time domain function can be this right-sided function or this left-sided function. And so you need extra information about the system to determine that which one is your actual impulse response. And say if we know the system is causal, then the RC should be the right-sided one, and you will have this impulse response. Okay. Get this. Okay. And then let's see a more physical example. Okay. So assuming so let's see a more physical example. So we have this RLC circuit, VRLC circuit, and so we have some driving voltage here, and a resistor, and inductor, and a capacitor, and we assume that the system is initially 0. Okay, so basically we assume initial race. Okay. The system is initially 0, and also basically we assume the system is causal because this is a physical system. Okay, so also causal. Okay, basically we assume initial race here, and then we try to determine how the system will behave with respect between the input and output. Okay, so we can write down the differential equation and I haven't said input output. So input will be the voltage here that drives the system, and the output we say is the voltage across this capacitor. Okay, and we can write down this physics equation. So the voltage here should equal to these three voltages adding together. So the voltage here is just Y, and the voltage for conductor will be conductor plus say the voltage for the resistor first. So voltage for resistor will be R times the current through it, and the current will be dy dt, and dy dt times the C, and then the voltage here, if you do the physics, will be LC d squared y dt squared. Okay, Anyway, so you see that if you do the physics correctly, you get this constant coefficient linear differential equation between y of t and x of t. Okay. And then we use our equation 9.133, and that's this equation. Then we just read through here. So this is some b sub s, and s to a k is just 1, and I guess here we actually divide LC to this side for some reason. But anyway, because it's highest order, you divide LC to the other side. So this side you have 1 over LC, and for other side you have this a squared plus r divided by LS plus 1 over LC. Okay. Anyway, so h of s is a rational function of s, and you can solve for point 0 for this, and there is no 0 because the upper part is just a constant. Then the lower part you have 2 poles. Okay. And you can kind of determine the property of the system by looking at the position of those 2 poles. Okay, and the position of the poles obviously will depend on the constants. So you have a constant R, L, and C. And but one thing you can determine pretty quickly is that if your R and L and C are all positive, then the poles, by solving this quadratic equation, you will have a negative real part. And here we kind of do a bit of calculation here, but you can also look at this problem to check it yourself. Just you solve the 2 roots of this quadratic equation, s squared plus r over ls plus 1 over lc equal to 0. If you solve this quadratic equation, then you will see that you will always have a negative real part. Okay, and that means that the system will be stable, because we already know the system will be causal because it is a physical system and satisfy initial risk, so it was causal. And this is an analysis that we have done before, that if all our poles of a rational system, or our poles of a rational function has a negative real part, then you pick the rightmost RLC, then this rightmost RLC will also contain a j omega axis. Yeah. So yeah. So this is what we said before, that if we have a rational system, and if we have a rational system, then if all is pole, I guess we had a bit different logic flow here, but basically if all our poles have a negative real part, then if it's causal, it will also be stable. I guess there are actually 3 things, and we say different things, but yeah, we say if it's both causal and stable, then all the poles will have negative real part. And but you can easily see that if a negative real part and it's causal, then it will also be stable. Okay, those 3 kind of 2 of them imply each other. Okay, so causality, stability, and all negative real part poles. Okay, and here are 2 possible distribution of the poles. So if a pole has some complex number, then it can look like this, and you have 2 real poles. They are both negative, and your RLC will look like this. Okay, so this is our ILC circuit, and we see that with this Laplace transform, we can get the system properties even without having. We can learn some system properties through this analysis on system function, even with just very general information. So here we only know that ILC are all positive, then we learn that the system is stable. So any ILC circuit, it should be stable. Okay, this is some very nice thing we learn from Laplace transform. Okay. And then let's see an example of we actually, I guess this is not quite differential equation, but we solve a little more. Okay, okay, so more example about learning system behavior from system function. Okay, so here assuming we have input output pair to an LTI system. Okay, So input is x of t is exponential decay e to the minus 3t u of t, and the output is y of t equal to e to the minus t minus e to the minus 2t u of t. Okay. And then once again, this is the LTI system, so we can analyze it by looking at it by doing Laplace transform and see how its system function look like. So with Laplace transform x of t to big X, and this is all very familiar. Laplace transform, you have e to the minus ATU of t with a equal to 3 here, so this is just 1 over s plus 3, and then it is right-sided, so pick the right-sided RLC. RE is greater than minus 3. And y of t, it has two parts, so you have this 1 over s plus 1 part minus this 1 over s plus 2 part. And if you combine it together, it becomes this 1 over s plus 1 times s plus 2. And once again, it's right-sided, and RLC is this greater than minus 1. Okay. And so from big Y and big X, then we can compute the big H. It's just big Y divided by big X. So it's this s plus 3 over s plus 1 times s plus 2. Okay, so we can determine we have determined the algebraic part of the system function, and now the harder part is we need to determine the RLC of this thing. Okay, and now we use the convolution property. The convolution property says that the RLC of this y should okay. So now it's a bit complicated. Okay, so convolution property says that we need to determine RLC of h, and we determine this by the convolution property because we know big Y is is equal to big H times big X from the convolution of small h and small t. Okay. And so convolution property says that RLC of y must at least include the intersection of RLC of x and h. And here, okay, so here the logic is a bit more complicated. So let's draw the point 0 here. Okay, so there are 3 different points. So there is this minus 1 pole, minus 2 pole, and a minus 3 pole. And we know, and there are 3 different RLC we need to decide. Okay, and so for y of s, we know the RLC is this greater than minus 1, and x of s, the RLC is greater than minus 3. Okay, okay. Let me see. I guess if I draw it down here, it will be kind of very messy, so let's not draw. Okay, and h of s, it has 2 poles on minus 1 and minus 2. Okay, and okay, and so the property says that the RLC of y must include at least RLC of x and h. And h can have 3 possible RLC because it has 2 poles. So the RLC can be greater than minus 1, or between minus 2 and minus 1, or less than minus 2. But we know, so now we need to analyze. So we need to analyze the RLC of, so the intersection between RLC of h and RLC of x. Okay, and and so there are 3 possible intersections. So the lemma's RLC of h will intersection with this RLC of x to be this between minus 3 and minus 2. And or in the middle one, the intersection between RLC of h and RLC of x is between minus 2 and minus 1. And let's see if the RLC of h was greater than minus 1, then the intersection with this thing will be greater than minus 1. And but you see that the RLC of y must contain an intersection. So for the first 2 cases, so there are 3 cases here. Let me try to draw more. Okay, so kind of a 3 line. Okay, so we kind of think what okay, I should have some name. So this is say this is Rx, and this is Ry, and we have Rh. Okay, and our question is what's intersection between Rx and Rh. Okay, and so there are three possibility for the three possibility of Rh. So it's either here, here, or here. Okay. And but we know Ry must contain this intersection. But you see, both of those choices is something outside of Ry, so you know they are both not correct. Okay, and so this intersection is not true. This is not true, and we know only this is possible. Okay, so although this is your intuitive pick, but here we do this very carefully. We have seen that the only possible RH is RH is greater than -1. Okay, so here we have done 3 case analysis. So RH can be less than -2 or in between. It has 3 possibility: less than -2, between -2 and -1, or greater than -1. And we will see that only this greater than -1 is correct. Okay. Okay. Yeah. So the only possible choice is RH being RES greater than -1. Okay. We okay with this analysis? This is quite complicated. Although you might see that, look at this very briefly and see this is right-sided, this is right-sided, and you want to pick RH to be also right-sided, and that will give you the correct answer. But if you want to do this carefully, you need to go through this analysis of looking at the intersection between RH and Rx. Okay, and yeah, so yeah. This is analysis. And I guess then here we have kind of a small question to keep people awake. And now I have seen the RC of RH, RC of H of S, then we can ask you where the system is causal stable. That will be keep doing. And so if you think the system is causal, raise your hand. With this RH greater than -1, is the system causal or stable? So if you are seeing the system is causal, raise your hand. And if you think the system is not causal, raise your hand. Okay, and yeah, indeed this is causal. This is causal because it's a right-sided RLC. And if you think the system is stable, raise your hand. Okay. And if it's not stable, raise your hand. Okay, yeah, and it is stable because it contains a geometric axis. Okay. And yes, here then we can say a bit of extra thing here is we can also do something that we'll do more is now we have this H of S, and remember we are talking about differential equation. So how this problem is related to differential equation is from this H of S we can also invert what we do in 9.133. Okay, so remember we have this thing, we say we have a differential equation, we can write down H of S. And now we have H of S, then we can also write down a differential equation. Although there are many differential equations that satisfy this, but we can write down one that's the simplest. Okay, so we can also write down a differential equation that's so we multiply this out. This is a squared plus 3s plus 2. So we have d squared y dt squared plus 3 dy dt plus 2y equal to dx dt plus 3. Okay, so from this H of S, we can find the differential equation, constant coefficient linear differential equation that will produce the same system function. Okay, so this is what we can do, and it will actually be very useful in terms of engineering. So maybe you know you have a system, you want to design a system with this kind of system, this system function, then you can convert this system function to a differential equation. Then you try to piece together different components to give you this differential equation. That we will talk about after we talk about these differential equation questions. Let's see whether we can get a bit to the block diagram. Okay. Yeah. Anyway, so that's this question, and that's the next question. Next question is even more abstract, so it's once again a detective question. So now I have a bunch of information about LTI system, and then ask you to determine the system function. Okay. So this is the kind of question that you can see in the exam or in your homework. Okay. So let's see through the conditions. So first one is system is causal, and then the second one says the system is rational and only has two poles. So I already told you the pole at -2 and 4. Okay, and from system being rational and causal, we already know that we can determine where the RC is. Okay, and then we have this kind of weird condition. This is an input-output pair. So input is x of t equal to 1, and the output is y of t equal to 0. Okay. And this one says that the value of the impulse response at t equal to 0 plus is 4. Okay, so this says that the h of t at 0 plus is 4. Okay. And yeah, so with this we want to solve the system function, so that's the h of s. Okay. And so let's just start the analysis. Okay, so I guess the most informative one is the second one. So from the second condition, we already know that we only have two poles, a pole at -2 and a pole at 4. And it's also rational, so it only has 3 possible RLC. So it's less than -2, between -2 and 4, and greater than 4. And then from its being causal, we know that you must pick the RLC that's greater than 4. Okay, so from those two, we basically already know most of the system functions. So we know anyway, so we know the RLC is greater than 4. Okay. And we also know it has two poles, so and it's rational, so its a system function already can be written in this form. So rational function is a polynomial divided by another polynomial, but only has two poles at -2 and 4. So we already know the lowercase is s plus 2 times s minus 4, and the uppercase is some polynomial of s. So we just write as p of s. Okay, so we already know all its poles. We don't know whether it's zeros are, and later on we are going to determine what is p of s, basically, and kind of determine where it's 0. Okay, and so that this is we are using the first condition and second condition, and we write down a pretty restrictive form of h of s. And now we need to use this weird condition: x of t equal to 1, then y of t equal to 0. Okay. And and how we use this is this is kind of weird, but how we use this is we remember that 1 is okay. So this is in time domain, and h of s is in frequency domain. So you might think it's kind of hard to determine to use this h of s from this time domain condition. But then you remember that h of s also have another interpretation. So in chapter 3, we say h of s is the eigenvalue of e to the st. Okay, and and how is this useful? Because you see that x of t equal to 1 is actually a special case of e to the st. Okay? So if you pick s equal to 1, then e to the st is, if you keep s equal to 0, then e to the st is e to the 0 times t. Then this is a constant for every t, and it's just 1. Okay? And yeah, so this is a trick here. So here we remember that h of s is also the eigenvalue of e to st, although we didn't use this in this chapter yet. But in chapter 3, where we say that h of s is big H of s is the eigenvalue of e to st, and we found out that s of t equal to 1 is a special case of this for s equal to 0. Okay, and and this being LTI system, then h of s is eigenvalue, then we have that h of 0 times this x of t should equal to output. Sorry. Yeah. So the output y must equal to h of 0 times the input x of t. Okay. So we know this input-output pair is e to the st at s equal to 0. This is x of t equal to 1 and y of t equal to 0. Okay. So then y of t equal to h of 0 times x of t. Then x of t is just 1, so y of t is just h of 0. Okay. And yeah, but y of t also equal to 0, so we know h of 0 equal to 0. Okay. H of 0 equal to 0, that means that 0 is a pole for this P of S, okay? Because, well, downstairs is nothing, yeah, so H of 0 equal to 0, that means that P of 0 equal to 0, and downstairs is also not 0, that's good, okay? And so P of 0 equal to 0, then we can write it as we can factor out a root for P of S, so P of S should equal to S. This is s for a pole at s equal to 0, sorry, a root at s equal to 0, and times another polynomial q of s. Okay. And finally, we need to use this weird condition that says that h of t at this t plus, h of t at this 0 plus equal to 4. Okay. And here we to use this condition, we use this initial value theorem we talked in section 9.5.10. Yeah. And so let's highlight this. We have an initial value theorem. Yeah. So the condition for is exactly the initial value of this time domain signal h of t, because we know the system is causal, so we know the system is causal, so h of t must be 0 for t less than 0, so we satisfy the condition we need for this initial value theorem. And at the 0 plus, this thing should equal to, from our theorem, so this 4 initial value should equal to s go to infinity, s times h of s. So s times h of s will equal to, from what we know, so s squared, so s times p of s equal to s squared q of s. So s squared q of s divided by the lowercase, this is s squared minus 2s minus 8. Okay. And when s go to infinity, this thing go to 4, then then you look at this, yeah, then you look at this, then you know that this will actually tell us what's q of s, because as s go to infinity, this thing go to, well, equal to some constant value, and the lowercase has highest order s squared, then the uppercase must also have highest order s squared. Okay, so that means that q of s cannot have any power of s. So q of s can at the most be a constant. Because if q of s has any power of s, this thing when s go to infinity will become infinity. So q of s can only be constant k, and then we put that back to this equation. You see that so you have k squared divided by s squared when s go to infinity equal to 4, and that must equal to 4. Yeah. And so we have determined we have determined our h of s through all those conditions, and such that, and that is h of s equal to 4 times s divided by s plus 2 times s minus 4. Okay. So this is a real complicated example, and you use whole bunch of pretty tricky property, and also has a delegate balance, so we're only able to solve Q of S because we know Q of S is only a constant, and the constant is specified by this initial value theorem. Okay, this derivation okay. Here the condition 3 and the condition 4 are a bit more tricky. Condition 3, you need to remember that h of s is the eigenvalue of e to the st, and condition 4, you need to remember that you need to realize that this is talking about initial value theorem, and we can use the initial value theorem because because the system is causal, so h of t equal to 0 for t less than 0. Okay. And yeah, so this is next example we want to talk about in this differential equation part. I guess we can have a bit of small review. So you see that I guess it's a bit of a mix of everything. But the start we said that you can determine the algebraic part of our system function by just look at the differential equation. So differential equation we have the summation bk is to a k divided by summation ak is to a k, and we'll get a rational function out of this. And then then from here there is a whole bunch of things you can do. You can infer your ROC by having extra condition of your system. So the most usual one is you say your system is LTI. So say like this. Say your system is not LTI. Say your system is initial rest. Initial rest implies that your system is LTI and causal. Then you can pick your ROC to be the rightmost ROC. Rightmost ROC specified by this rational post, and you have determined your system. And we also see that by just looking at the system function and thinking about the property of ROC, you can learn a lot about the system. You can learn about a lot of the system characteristics, and mostly whether the system is stable or not. A causal system. So, for example, whether a causal system is stable or not. So here we have seen that this system is causal and will also be stable, and here we also have a causal stable system, etc. And we can have more analysis, more tricky analysis of system function, like in this case. We can determine system function by this kind of very complicated detective work. And let's go back here. So here we also say that if we have some system function, we can write down a differential equation for it. And this is a very useful thing to do in engineering because, well, you want to build a system that has some particular kind of system function. Say maybe you want to build a filter or not, or something. So this leads us to this quick introduction. So we only have 5 minutes. So I guess we will continue a bit more next time, but I want to start a bit. So this can be done by analyzing those block diagrams. Okay, so we can analyze block diagram to to calculate its corresponding system function, and we can also design some block diagram for some system functions. Okay. So let's see how this works out. So we have those system function, and we can connect block diagrams in those component systems in different ways. So in chapter 1, we talk about there are different interconnection between systems. Like you can have this parallel connection, or you can have this serial connection. So parallel connection, you split the signal into 2 and add together, and parallel you go through first system and go through the second system. And we can think about what's the small h and the big H for the corresponding system. So you have the total output, input output is x and y, total input output is x and y. And we can think about how x, y is related by some small h or by some big H. And small h is pretty simple, and I think we have seen them before. So the small h for this total system will just be by linearity of the system. It will just be small h1 plus small h2. And so if you do Laplace transform on this small h, then you see big H is just big H1 plus big H2. And a bit more. Okay, so that's this system. And for this system, we have seen that by the property of the convolution, if you go through some small h1 system and go to small h2 system, then you are convoluting with small h1 and convoluting with small h2. But by the associative rule, associative rule of convolution, then this is just x convoluted with this small h1 convoluted with small h2 first. So these two systems together can be viewed as a system with small h being small h1 convoluted with small h2. And now using convolution property, so you do Laplace transform on this, then you see that big H is equal to big H1 times big H2. Okay. And for now, we kind of ignore the RC and just look at the algebraic part of the system. And for RC, you need to determine that later. Okay, so here we are just trying to do those calculations for the algebraic part of our Laplace transform. Okay, so we have this parallel connection and the serial connection, and see how the big H transform. So parallel connection, big H will just add together, and serial connection, the big H will multiply together. And now we consider something more complicated, that's a feedback network. Okay, and so we have feedback network. So we have some big H1 and the big H2. Then we can think about how this feedback network give you the total big H for this feedback network, feedback interconnection. And so we basically need to list out the equation at each point. So at this point, you have big Y equal to big Y equal to it's through this block. So this through block, the output will be Y, and big Y will be this big E. So this thing just after this feedback point, big E times big H, because we're talking about this serial connection. So it goes through this big H1, then this output big Y is equal to big E times big H1. And and at this point, you will have big E equal to big X, subtracting this big Z. So this point we say is small z or big Z. And at this point, through this block, we have big Z equal to H2 times big Y. And so if you string all those relations together, you can eliminate. So you want to eliminate big E and big Z, and you want to get a relation between big Y and big X. And you will get big Y equal to H1 times X minus H2 times Y. And you move things around more, because it is linear in both Y and big Y and big X. And you can see big Y divided by big X, which will be the big H, will be H1 divided by 1 plus H1 plus H2. Okay, and so sorry for going over time. This is a bit of how we have been going, looking into a bit of how the block connected diagram will work. And next time we'll talk more about this, and we'll talk about unilateral Laplace transform. Okay, we'll give you more detail about what we can build with this block diagram and feedback interconnections. Okay, so see you next Monday. Okay.